So in this video, what we're going to start talking about is we're going to be talking about vector functions or vector valued functions and space curves. And so, and this is actually going to be the topic for the entirety of this section of this chapter. One thing that I want you to get before we start with vector valued functions is that the concept actually is not all that terrible. Once we start working with vectors, okay, we can do calculus on vectors. And basically, we're going to do calculus on vectors by working with each component, one component at a time. That's pretty much it. And how those components are going to work is they're going to work like parametric curves, right? So you got an x value, and that x value or x component is going to be parameterized using the t or an s or something along those lines. And then you'll have y, and that'll be parameterized with the same t, and the z is going to be parameterized with the t as well. So pretty much what it's going to look a lot like is a lot like parametrization. And in fact, our graphing is going to work identically to parametrization, okay? And basically what we're going to be imagining is we're going to be imagining that when we draw a space curve is, we're going to draw the space curve, you know, essentially where if you imagine you've got a vector, the end of the vector, the terminal point of the vector is the edge of the space curve. So we anchor at 0, 0, 0 or 0, 0, and then we draw a vector out, and that vector, that point is going to be on the space curve. And then that space curve is basically going to kind of show us essentially what the terminal points for all of the vectors in the vector valued function are. All right, and essentially that's it, right? So you could go, oh, okay, well, where is this vector going to go? It's going to go right here because that's the so that's the line that goes from the origin out to the space curve. Okay, so what I want you to get is that essentially you're going to be utilizing all the tools and techniques that you have used for calculus thus far. That's actually one of the cool things about doing all this vector calculus is because you don't really need to relearn anything. You just need to like add a wrinkle in, okay, and then learn how to conceptualize things just slightly differently, and then otherwise it's just calculus. It's the calculus you've always done. So here's our definition, and this is coming from Calc 3. It's Strang and Herman. That's the book that I use. And so it's a vector valued function is a function of the form r of t equals f of ti plus g of tj, or r of t equals f of ti plus g of tj plus h of tk. All right, and then we have an alternative. We can call it a component function. And the component function looks like a vector, except for the x and y terms, right, are functions. There's your x, there's your y, here's your x, here's your y, here's your z, okay? So basically what's happened here is that instead of having vectors that are single valued vectors that have single values, the values for your components are going to be variable. They're going to be based upon functions. All right, could those be constant functions? Totally, they totally could. But for the most part, they're going to be functions. And what we're going to imagine these functions as is kind of like they're going to be basically parametrizations. Okay, so the parametrization is going to be x equals something, y equals something, z equals something. And we're just going to write them, right, as f of t, g of t, and h of t, right? Or we might even write them as x, y, and z. Or x and y. We write them in component form to represent the fact that what we're going to do is that when we draw our space curves, or when we think about particular values, okay, for a value of t, an input of t, we're going to get an output, right, okay, that gives us a vector, all right, and hence why it's called a vector valued function is because when I input t, instead of just getting a single value back, I'm going to actually get a vector. And that's one of the big ideas here. So let's suppose that we have r of t, and notice that over my r, I've put that vector symbol. And that actually identifies that what I'm looking at is I'm looking at a vector function. Notice also I have I and j here, and then I have two functions of t for my components. Okay? And if I wanted to rewrite this as a component function, I could write it as r of t equals, and this would be 4 cosine t, comma, 3 sine t. Okay, so what I want to do now is I want to go through and I want to determine the domain and find the values of the vector function at 0, pi over 2, and 2 pi over 3. Okay, and they're going to operate just like we're working with functions or parametric functions, parametric equations with values 0, pi over 2, and 2 pi over 3. So first, determine my domain. what I'm going to do to determine the domain is, okay, so the domain is the intersection of the domains of all of the components. So basically what this means is that we cannot select a value for t that doesn't work in each one of the functions for the components. So if I look here, I've got 4 cosine t and I've got 3 sine t. And so the domain for 4 cosine t, okay, that domain is going to end up being all real numbers. And then the domain for 3 sine t is also going to be all real numbers. Now, since both of them have all real numbers as their domains, the domain for r of t is actually also going to be all real numbers. I can select anything that I want, and this should be for t. Okay, so t can belong to all real numbers. We can actually write that. And that's fine. Okay, because the intersection of all real numbers and all real numbers is just all real numbers. Okay, so we do want to actually make sure that we are inputting values in for t that we can actually give us, you know, determinate or defined values for our functions. So that's the first thing. The second thing now is to find, say, for example, r of 0. Well, r of 0, and if I write it in component form, is going to be 4 cosine 0, comma 3 sine 0. So all I'm going to do is I'm just going to plug in 0 into the function. And this gives me then 4, because 4 times 1, and 0. So 4, 0 is the result for the vector valued function at 0. We'll find r of pi over 2. And so that'll be 4 cosine pi over 2 and 3 sine pi over 2. And so consequently, 4 times 0 is 0, and 3 times 1 will end up being 3. So that's 0, 3. Finally, we'll find r of 2 pi over 3, and that's going to then be 4 times cosine of 2 pi over 3, comma 3 sine 2 pi over 3. Remember that our cosine is going to be negative in that quadrant, so this is going to end up being 4 times 1/2, or negative 1/2, and then 3 times square root of 3 over 2. And so what we're left with is negative 2, comma 3 root 3 over 2. So basically what's going to happen here is we're going to input a value of t, and then we're going to output, we're going to get an output is one of the components, okay, until we get all the components of the vector. So a vector valued function in 3 dimensions is called a space curve. And so space curves, though, we're going to graph space curves in a very similar way to the way that we actually graphed our plane curves. Right? Plane curves are 2-dimensional, space curves are 3-dimensional. So what we're going to do is we're going to construct a picture here. I've got x, I've got y, and I've got z. Or we can call it I, j, and k. Actually, why don't we do that this time? We'll call it I, j, and k, just to represent each component. And I'm going to start out, I'm going to go from 0 to 4 pi. So I'm going to have 0, I'll do a pi over 2, a pi, okay? Probably have a pretty good sense of what's going to happen here. By the way, notice that I've got 4 cosine t and 4 sine t. So this is going to be a lot more circular. This is not going to be elliptical because there's no eccentricity. We don't have a different value in front of the sine and the cosine. And then I'm going to kind of, you know, once I get a sense of what's going to happen as I go around once, 3 pi over 2, 2 pi, then I actually want to think about, okay, what about 3 pi, and then finally maybe 4 pi, okay? So what's going to happen, we'll start out, we'll plug in 0. So we want to find r of 0. So r of 0, I've got 4 cosine 0, that's 4. 4 sine 0, or 4 sine of 0 is going to end up being 0. And then k, since for our kth one, t is just going to be t, this is going to be 0. So my first point, okay, is going to start out here. If we just imagine 1, 2, 3, 4, there we go. So at 4. Now what about pi over 2? With pi over 2, 4 cosine pi over 2 is going to be 0. Then we're going to go to 4, okay, and then my k value is now going to be pi over 2. So it's going to be like 1.7. So what does this mean? Well, I'm going to be at, on the y-axis, I'm at 4, okay? But, or at 0, 4. So 0 in the x direction, 4 in the y direction, and then we're going to go up like 1.5. So what's going to happen here, here's that second vector, if you want to kind of imagine that. Here's my first vector, and I'm going to imagine that I just have some lines connecting those vectors. So basically, this is circular because it's cosine t and sine t. So we're going to move up. And so the circle, we're going to get a circle, okay? But the circle is going to actually be climbing along the z-axis as we go around the circle. Now, let's take a look at pi. I plug in pi. This ends up giving me -4. When I plug in pi into sine, that's 0. So 4 times 0 is 0. And then finally, pi, for tk, I got pi. So now I'm going to be, right, I was kind of up here. Now I'm going to be, I've got 1, 2, 3, 4, okay, in the, or -4 in the x direction. And then I'm going to go up pi. So pi is basically double up. And so now I'm moving up my circle. Okay, there we go. Now what about 3 pi over 2? Well, 3 pi over 2, cosine of 3 pi over 2 is going to be 0, so that's 0 again. Sine of 3 pi over 2 is going to end up being -1, so this is -4. And then 3 pi over 2, we're now continuing to climb in the z direction. So now my vector valued function is over here. It's got -4 in the y direction. Okay, and then I'm going to go up 3 pi over 2. So 3 pi over 2 is going to be about 4.5. So like it's kind of started to climb again. Okay, climb-ish. So there we go. Then we go to 2 pi. Okay, so 2 pi, that's going to take us back around to the beginning in terms of our values for cosine t and sine t. And so essentially we're going to have 4, 0, but now my z is different. My z value now is going to be 2 pi, which is like 7. And so now what's happened is you just imagine that I am directly above this point or this value. So you're kind of moving along here, you're actually moving up. And we're going to then, this is a little strange, but here we go. We're going to kind of move up to the 2 pi range, so it's about there, if we kind of imagine that. And the weird thing, to get this to kind of look right, we kind of have to circle in on ourselves. Okay? So what's going to end up happening is we kind of do one of those things, and it's moving upward. So basically, to give myself the kind of the illusion of what's happening here, right? I've moved upward, and then I'm going to kind of circle back around, okay? Because actually, we have increased the circle, right? It's just because we've got to kind of create an optical illusion here to see that circulation, things moving circularly around that z-axis. It's become a little bit tricky, but that's basically what's happening with this graph, okay? And if we look actually with 4 pi, if we went to 4 pi, cosine of 4 pi is going to end up giving me 1, so this is going to be at 4, okay? And then 0, but now at 4 pi, so it's actually kind of moved quite a lot up. So what's happened here is we constructed a path, and that path is going to move around in a circle on the xy plane, but then it's going to move upward in the z. Okay, I'm sorry it's not perfect on that end, but that's basically the idea. The z's are increasing, right? You see, here's my k values for my function. They're all increasing, and the i's and the j's, they're just moving around in a circle because it's cosine t and sine t. Okay, and so finally, actually, we're going to end up right here. So we can actually stop our curve right there, because that's when t equals 4 pi. So right here, this is t equal to 0, and then t equals 4 pi is at the end of that. And notice as well here, something we didn't do on the last one, but I can go back and I can show you, is that we actually have an orientation. Okay? Basically, we're showing how it is that we progress along the space curve. Okay? So when we're drawing space curves, like plane curves, we're basically going to construct a table, put in values in the table, and then kind of draw it out and see if we can create an entire picture of this particular vector function. And all we're looking at, we're not going to draw all the vectors. Instead, we're just going to draw their terminal points. And the space curve is going to be a capture of the terminal points. So basically, vector valued functions, and when we graph them, they are parametric equations. And they have values for our x and y and z, or our x and our y, depending upon whether or not we're using a plane curve or a space curve. Now, it goes to say, just like when we were working with parametric equations and parametric equations, is that there's a lot of different ways to parametrize a set of functions. Depending upon how you want to place t, and you want to create the relationships between t and the other values, the x's, the y's, and the z's, you can come up with a lot of different parametrizations. And these are called reparametrizations. And they give you the exact same function, because they give you the same exact values for functions, just sometimes they're easier to work with. And we're going to see some places where we might actually end up with, reparametrizing something or reworking something where it ends up becoming a lot easier to work with. And so that's something that you want to kind of keep in mind as well. One of the other skills that we might actually need to do is we might not need to actually find the curve of intersection for two space curves. That is basically, if we have, say for example, in this case, a cylinder, okay, and a surface, z equals x squared plus y, what is their curve of intersection? Like, where do they intersect? All right, it could be a line segment, it could be, an entire curve. And what we're interested in is we're interested in figuring out what that is in terms of t. So we're going to parametrize the curves in terms of t, and then we just want to make sure that the functions work for both. If we constructed them correctly, we're going to get a parametrization where we're going to get both functions in terms of this t, and so hence that means that they must be their intersections. So I'm going to look at x squared plus y squared equals 1. And if I think about this, this is a Pythagorean triple. If I let x equal cosine t and y equals sine t, that's my traditional relationship here, okay? Especially because 1 is the radius of that circle, the unit circle. What do I get? I get cosine t squared plus sine t squared equals 1. And that is exactly that curve. That's the cylinder. That's the parametrization for that cylinder. Now I just need to figure out this other one here, but it's pretty simple. We're just going to have z, and I'm going to plug in x and y. So that means z equals cosine t squared plus, in this case, sine t, or cosine squared t plus sine t. And that is actually the intersection of those two space curves. This parametrization here, x equals cosine t, y equals sine t, and z equals cosine squared t plus sine t, in fact, give us the intersection of those two curves. Pretty simple, okay, in terms of finding that intersection, and that's essentially what you're going to be doing. So the last thing that I want us to talk about is I want us to consider this vector valued function, and I want to talk about transforming it back into rectangular, or back into our Cartesian coordinates, because actually we can. And if you remember, this is our helix, and so consequently it's kind of circular, it's moving upward along the z-axis, right? It starts 0, moves in a circular direction, and it's going to move upward. And so what we want to do is we actually kind of want to think about this in terms of parametric equations, and we can then turn this back into rectangular coordinates if we wanted to. So I've got x is going to equal 4 cosine t, and I have y is going to equal 3 sine t, and then I have z is equal to t. And so I want to turn this into rectangular, or Cartesian coordinates, or unparameterize it basically. And so what I know is I have that z equals t, and if z equals t, then that means that I have x is going to equal 4 cosine z, and y is going to equal 3 sine z. Okay? So this is actually, it's got kind of like, it's elliptical. It's actually going to end up being elliptical, and we're going to see why in just a second. So what you notice, you have a cosine term and you have a sine term, and if you have cosine terms and sine terms, you will know that a Pythagorean identity is actually going to be really handy for us, right? We do know that cosine squared z plus sine squared z is going to equal 1. That's always going to be the case, right? That is the Pythagorean identity. So what we can do here is we can take these two, okay, and we'll make x over 4 equal cosine z, and we'll have y over 3 equal sine z. Okay? And so given that's the case, what that's going to then give me now is that's going to give me, I'm going to use this Pythagorean identity. I'm going to get x over 4 squared plus y over 3 squared equals 1. Or x squared over 16 plus y squared over 9 is equal to 1. Now, in 2 dimensions, this actually ends up being an ellipse. And that's why, for example, this here, that was the parametrization for the ellipse that we saw in 2 dimensions when we had the plane curve. For the space curve, which is the helix, and if we imagine we're moving upward, right, as an elliptical helix, okay, this ellipse, it has an x term and a y term that gives me that elliptical shape, but then the z term, which is not located inside of this equation, right? Z can be whatever we want. That z term, okay, is what's going to allow us to move up and down, okay? And so consequently, what we get is we get the equation in rectangular. Now, one thing to actually kind of get about this, and it's a little different, a little strange. This actually is missing information. If you think about it, it's actually missing info. And the info that it's missing is that the value for t, or our value for z, is actually changing. Okay, it actually changes as we change our space on the ellipse. So while this function right here, okay, is in fact like an elliptical cylinder, okay, that's going to end up being an elliptical cylinder, this parametrization right here, okay, that's going to actually give us the helix, okay? And so what you kind of see here is that your parametrization is actually going to give you some extra information that's going to actually allow you to graph a curve more fully. So what that does for us is that finishes up our conversation on vector-valued functions. We're going to do more work with vector-valued functions, and we're going to be looking at the dot product of vector-valued functions, cross products for vector-valued functions, and also calculus on vector-valued functions, limits, continuity. But really, all of that is going to, it's going to kind of follow some very familiar rules. Like finding the dot product, you're just going to use the calculations for the dot product. Finding a cross product, you're going to do the same. When it comes to differentiation and integration, we're also going to pretty much do the same thing, except we're going to be finding the integrals or the derivatives one value at a time. We'll get some special rules that will help us as we do more work with proofs. But for the most part, it's going to look, for what we're doing right now, it's going to look very similar to working in calculus when we just had functions in 2 dimensions. So we'll talk about that more in just a moment. Okay, so this completes the lesson. Remember today, what we've got here is we've talked about what a vector-valued function is. Okay, we discussed parametrizations a little bit more, and we also talked about graphing plane curves and graphing space curves.